All right, here we go. Fun in the sun. And this is not talking about going a mile from my house and going to the beach in Florida. This is about advancing the exploration of space weather. Welcome back. Hope you all enjoyed the last session with Nikki Fox. She said some things that are applicable to this session, and so it leads right in. The description of the session is that heliophysics research and exploration focuses on studying the sun, the heliosphere, and planetary environments as elements of a single interconnected system, one that contains dynamic space weather and evolves in response to solar, planetary, and interstellar conditions. And that's all one sentence. We've got a panel that is really going to be interesting as we go through this. Our moderator for this panel is Nicole Duncan. Nicole is the mission area lead of heliophysics at Ball Aerospace. Nicole, please introduce your panel.
Hi, thank you, Alan, and thank you, everyone. Welcome to the 2021 Goddard Symposium panel on advancing the exploration of space weather. Joining me on the panel today is Dr. Antti Pulkkinen. He's the director of the Heliophysics Science Division at NASA's Goddard Space Flight Center. And there he oversees a diverse research community that spans all disciplines of heliophysics and also hosts the Community Coordinated Modeling Center that provides space weather analysis and modeling support. His research has included things like ground effects of space weather and complex nonlinear dynamics of the magnetosphere-ionosphere system. Also joining us is Dr. Nour Raouafi, who's the project scientist of NASA's Parker Solar Probe mission, which launched in August of 2018. Hi, Nour. And it's the record holder for the closest man-made object to a star and also the fastest spacecraft, having recently reached 330,000 miles per hour as of May of this year. Nour's research spans a wide range of solar and heliospheric topics with an emphasis on the dynamic solar corona. Also joining us is Dr. Elsayed Talaat. He is the director of the office, hi Elsayed, it's Office of the Projects Planning and Analysis for NOAA's Satellite and Information Service. In this role, he provides leadership and oversight of many elements, including the development, acquisition, integration, installation, and acceptance of major subsystem elements for NOAA's environmental satellite systems. Before joining NOAA, Elsayed was the chief scientist of the Heliophysics Division at NASA headquarters, program scientist for the Living with a Star program, supervisor of the planetary and Earth atmosphere section at APL, and his research has highlighted geophysical and planetary phenomena. So welcome to our panel. Space weather is a dynamic and rapidly evolving field where new discoveries continue to shape our understanding, such that the connection between research and operations is vital. Also evolving is our nation's understanding of the importance of space weather through recent legislation like ProSwift and its commitment to protecting life and property through investment in research and operations. In today's discussion, we're going to center around how future observational architectures will enhance our understanding of modeling and forecasting abilities for space weather. The panel will explore why we need to expand our ability to forecast space weather events and what sensors, models, observations are needed in order to enable that next generation architecture. Each panelist will give us a short presentation on their thoughts of this overarching topic, and then we'll have a discussion session. I have a few questions to get us started. We'll move through considering what open questions exist, discussing recent discoveries, and then learning how to take these new results and incorporate them into future architectures. As we go along, please enter your additional questions and we'll address them at the end. So let's get started. Can you please pull up the slides? And I think Antti is first up.
All right, thank you, Nicole, and thanks for the committee for the invite to participate in this panel. This is a great honor. So I will share a few thoughts in terms about the future of heliophysics, and then also a few specific words about the space weather. If we had the next slide. But before going to discussing the future, let's look where we are and where we have been. So these are the top level objectives from our current decadal survey. You heard Nikki talk about a lot about our current, next decadal survey. But these are the top objectives from the one that we are still executing at this time. If you could, you can see here that we're dividing our field into three sections, if you will. From the top, the first major objective is to explore the fundamental mysteries of heliophysics, really drill down into those fundamental physical processes that operate throughout the heliophysical system. The second goal there, or objective there, pertains to understanding the linking between different fundamental physical processes that operate throughout the heliophysical system. For example, understand how these solar eruptions interact with the planetary magnetospheres and how they dynamically change, for example, the near Earth space environment. And then the third objective there at the bottom is really fundamentally space weather. So the objective is to take the new understanding about the fundamental processes, a new understanding about the linking between different heliophysical domains, and enhance our understanding, our exposure to the space weather hazard. And also to take that fundamental understanding about these physical processes and use that to mitigate those hazards. So in a sense, you could say that at the objectives level, space weather is one third of the heliophysics. And I think this overall approach per the current decadal that has the fundamental research at the top, and then you have this flow of information and capabilities going through the pipeline and eventually through research operations pipeline that can help organizations such as Elsayed on the Nour side. So this is how we've been operating so far, and I think there are a lot of good elements here that I hope to see also in the next decadal survey. If we could go to the next slide. And the core message here is that, but that's not really up to me. It's up to the community. And as Nikki very well explained earlier in her earlier talk, we are right now in the middle of the gearing up with the next decadal survey process. And this is the opportunity for the community to tell what the future of heliophysics and also space weather should be looking like for the next decade or next several decades moving forward. Nikki also mentioned that one of the key activities to these pre-decadal discussions, which is the Heliophysics 2050 workshop, is actually ongoing as we speak right now. So this is a very opportune time to have this panel. I was actually attending the space weather focused session just earlier before this panel here, and it was absolutely fascinating to see the community engagement in the process and all the great ideas that people have and are wanting to put forward in terms of white papers that will be entering the decadal process itself. So the key message here is that it's community's time to voice their thoughts and vision for the future of space weather as well. If you could go to the next slide. But with that said, I do want to share, maybe a few very high top level thoughts from our organizational standpoint, from the standpoint of the Heliophysics Science Division at NASA Goddard Space Flight Center. And what I want to do here is to share actually a few items that I shared with my division just a couple of months back in one of our division town halls. I'm not going to labor all of these points here, but there are a couple of things that I do want to highlight, and the things that I have also emphasized to our own organization at Goddard Space Flight Center. The one of these points pertains to the culture of innovation. I think we need to establish even stronger culture of innovation. We need to be able to think even more outside the box. We need to be able to dream even bigger, and then maybe even take a little bit more risky, or have a thoughts about the instrument concepts, science investigations, and missions that are a little bit more risky. And coupled with that is very closely the idea of diverse, equitable, and inclusive workplace. And this is also something that Nikki very, very nicely highlighted in her piece. And we do agree with this. We need to establish even more diverse, equitable, and inclusive workplace. And this is some of the key areas that our organization at Goddard will be focusing on moving forward. And of course, in my mind, I know this is very closely coupled with the idea of culture of innovation. As we bring in more diverse workforce into the organization and to the field in general, that will lead also to diversity of ideas and to the new level of culture of innovation that we can culture in our organization and hopefully across the community. So with that, I will end my opening remarks, and I look forward to the Q&A portion here. Thank you, Nicole.
Thank you, Antti. I think the next slide deck is from Nour. Can you please bring that up?
Okay, thank you, Nicole. And I want also to thank the organizers of the Goddard Symposium for the invitation to talk about a subject as important as space weather and how to advance our knowledge to live in harmony with our gentle star, the sun. Antti put in perspective space weather really well and made my job easy in a way. Next slide, please. As we depend on space more than ever, be it for our daily lives or for exploration, the importance of space weather is increasing at a fast pace. Soon, we are going to land women and men on the moon again, and hopefully on Mars soon after that. We need to have all the knowledge to protect them. We can rely on technology for that purpose, but preventive measure can be extremely helpful and can potentially be cost-saving as well. The fact of the matter is that we live in the immediate environment of a magnetized and highly active star, and explosive magnetic activity in the solar atmosphere can affect us in many different ways, and sometimes it can affect us in an adverse manner. Next slide, please. The geomagnetic storm caused by a solar Carrington-like event on March 13, 1989, is an excellent example of what we can expect if one of these huge events erupting from the sun hits Earth head-on, or it can affect a human in space. What you can see here is a power outage spreading throughout the northeast of Canada in the US. This lasted for several hours, I believe, or even a good part of a day. Now, imagine this happen on a more global scale and lasts for weeks and potentially for months. We are looking at colossal losses. We may even have a partial collapse of the economic system. And the impact of that, it will be on all of us. It will not be selective. Next slide, please. The sun plays a central role, obviously, as a primary driver of space weather. What you are seeing here is numerical simulations from CCMC at Goddard, showing how our geomagnetic sphere reacts to solar events of different strengths. All our space models rely on solar observation directly or indirectly. This is one of the many reasons why we need to understand how our star works and to prevent its rot. Next slide, please. As far as the sun is concerned, there are two aspects to space weather. There is the forecasting aspect of it, but there is also the modeling space aspect of it. As I said, the first aspect is about forecasting of solar explosive events such as flares and CMEs, and particularly the big ones of them that can affect us quite a bit. In terms of advances, I would say we are not there yet, but we are advancing toward that goal, particularly in view of space missions like Parker Solar Probe and Solar Orbiter that are flying in regions of the heliosphere that we never visited before, and they are making breakthrough discovery, leading us to understand how the young solar wind behaves, and also how the early stages of these explosive events on the sun evolve. There is also the largest solar ground-based telescope, DKIS, that is being built in Hawaii. It will be operational hopefully next year. This will provide us probably the best observations ever of the solar magnetic field. So with this cutting-edge technology in terms of observations, we are going to make significant progress toward understanding what triggers solar events, and mainly the pre-eruptive signatures that tell us that something is about to happen. For this, we need continuous multi-wavelength, high-resolution, high-cadence data. And obviously, as I really insist on continuous multi-wavelength, high-resolution, high-cadence. We need all of them at once. Next slide, please. The other aspect of space weather from the sun is the modeling. One key ingredient that we needed for all our models, solar models that deal with space weather, is the magnetic field. But the issue there is that at a given time, from one vantage point, we can only see one hemisphere of the sun. And one big problem is that we always find ourselves driving our models with a month-old data. And that is a big, big limitation. Here we need to change the way we observe the sun. And to solve this issue, we need to watch the sun as a whole. We need a 4-pi constellation around the sun that is providing data from all faces of the sun. To conclude, space weather is more important than ever. It's also a more complex problem. It's a very complex problem that involves many coupled systems going from the sun to Earth and beyond. We may not make the breakthrough advances we hope for unless we invest big. And this is really, I have to insist on investing big because it's a huge problem. With this, I yield and go to the next, to Elsayed.
Thank you, Nour. Can we pull up Elsayed's slides, please?
Thank you. I also want to thank the organizers for inviting me to give NOAA's National Environmental Satellite Data and Information System, or NESDIS's update. I'm pleased to give this update and show how in some ways we are implementing the last couple of decades of space weather research into operations. Let's go on to the next slide. The first thing I want to communicate is that in the last year or so, NESDIS has established space weather as a third pillar of environmental observations alongside low Earth orbit and geostationary terrestrial measurements. And our space weather strategic objective is to advance space weather observational leadership in all applicable orbits to meet our mission needs. This includes continuity of space weather observations that we currently make right now in an ad hoc fashion, and innovation around satellite systems, and as I've described, including the Space Weather Follow-on L1 mission, and partnerships to collect and share data for use by customers. Our key partners, including, of course, academia and commercial industry, are also our interagency partners at NASA and international partners, EUMETSAT and ESA. That collect and share data with us on space weather phenomena. And then our main customer is the NOAA Space Weather Prediction Center that serves a diverse user communities. Next slide. So we like to split our perspective into 3 different orbits, going from closer to further from right to left. We start with low Earth orbits, in which each satellite can cover a large part of the Earth twice a day. It allows in low Earth orbit allows high resolution multi-instrument observing systems. Pole-to-pole coverage. These are essential delivery to our numerical weather prediction for neutral atmosphere, but also for ionospheric models going forward. And low Earth orbit allows a dense concentration of satellites. Examples in this include the Cosmic 2 satellites that are providing ionospheric occultations in a very dense manner at low and mid latitudes. As well as radio occultation partners we have for the high and mid latitudes. In geostationary, we can have continuous monitoring, the same geographic image over global coverage through shared systems, with a geo ring of partners around the globe, and extremely low latency for real-time applications. So for the solar and particle information that are able to obtain. That has needs very quick delivery to space weather users. And in deep space, NOAA is committed to the Sun-Earth line for the L1 observations upstream of Earth and real-time solar monitoring as well of imaging and coronal mass ejections and imaging of coronal mass ejections. L1 provides an uninterrupted view of the sun and the solar wind with extremely low latency with ground from space to ground connection. And then next slide. And to continue the continuity of critical space weather data on the Sun-Earth line and flow to Space Weather Prediction Center, we have developed and are implementing the Space Weather Follow-on Program. This is comprised of 2 flight projects. The first is development of a compact coronagraph that will launch on the GOES-U spacecraft into geostationary that will launch in 2024, and the development of a Space Weather Follow-on L1 mission that will operate at L1 point upstream of the Sun-Earth line and carry a compact coronagraph and in situ instruments to measure the magnetic field and particle environment there. Together, GOES-U and the SwiftWell-1 will provide a robust observation of space weather along the Sun-Earth line and continue that for NOAA succeeding Discover, the NOAA Discover and the NASA ACE satellite, and SOHO and ESA NASA SOHO satellites. Next slide, please. So in final slide here, just want to convey that we are planning a new space weather program that will encompass diverse observation requirements. And we know that space weather, as you've heard and will hear, that it must be made from diverse vantage points in LEO, HEO, L1, on off the Sun-Earth line axis. And this program will subsume the Space Weather Follow-on program that I just described, but main continuity of hosted space weather instruments that we have currently in geostationary and in low Earth orbit, such as Cosmic 2 and NOAA POSE. The need dates and to maintain continuity and improve our capability are varied, but we are starting to plan from from the program of record that we anticipate in 2025, which includes the SwiftWell L1 mission, the space weather instrumentation on the GOES East and GOES West spacecraft, Cosmic 2, the NASA Gold, which you heard about, as well as our partners with EUMETSAT for low Earth orbiting particle instrumentation and radio occultation, and ESA, which we anticipate we are partnering with to provide off Sun-Earth line axis, Sun-Earth axis measurements at L5. And that's it for now. Thank you.
And thank you as well. Okay, so we're going to move into the discussion portion of our panel here today, and thank you, the 3 of you, for setting the scene for all of that. So my first questions are for Antti. From your vantage point as both a director of a broad research community at Goddard and then also as a space weather researcher yourself, can you comment on what key gaps exist in our knowledge and ability to model space weather?
Well, thanks, Nicole, for that question. And of course, I emphasize again that that gap analysis sort of is being done by the community right now as a part of the decadal process. But I will, of course, be happy to share my personal thoughts here. I think and I'm pretty sure that a lot of the community would agree with this as well. I think we really need to make a new push to system science approach to model the space environment system. We know that all the different domains, starting from the solar convection zone all the way down to the mantle of the Earth, these are highly complex and coupled systems, and we need to have a systems approach to be able to really in a predictive manner model the evolution of the system. Another key area I think where we really need to make a big push over the next decade is to introduce data assimilation as a standard part of the modeling that we do. Of course, we have some very specific challenges pertaining to the data assimilation if you compare to the lower atmospheric weather community. Our domain is much more sparsely sampled, And a lot of the techniques that the lower atmospheric weather community is using for the data assimilation purposes do not necessarily pertain directly in our application. So that's another area actual fundamental research that still needs to be pushed further before we can take full utility of the data assimilation in our couple systems modeling approach. And the final point I do want to make is that we also need to start looking at seriously at the AI and ML, artificial intelligence and machine learning techniques. They're not the magical silver bullet that will solve everything that we're doing, but it is a new advanced tool in our toolbox that we really need to be leveraging heavy moving forward in terms of doing the systems science approach, assimilating data and using the advanced AI ML techniques to further enhance the modeling outcomes from our future models.
Thank you for those thoughts. And absolutely, I've heard a lot of those themes come up this week at Helio 2050, and then also through a lot of the pre-discussions that the community has been having as well. And so do you have any thoughts about what missions are planned or which ones are needed in order to address those gaps that you called out there?
Well, Nikki gave a really great overview of all the missions that are being implemented being developed, implemented, and are soon ready to go out there, and that's just an amazing portfolio of missions that will help supplement the Heliophysics Systems Observatory. And then, of course, we have some of the new strategic level missions that are being in development. For example, Geospace Dynamics Constellation, or GDC, is a good example of that. And GDC is destined to really revolutionize our understanding of the ionosphere, thermosphere, mesosphere system, and ultimately also lead to types of enhancements on the data assimilation side of things that will push our predictive capability in terms of the ITM system to the next generation. From my personal perspective, and I think these are the kind of themes that have been coming up throughout the week and also in the Helio 2050 workshop, is that because of the complexity of the heliophysics system, we need to be able to sample the spatial and temporal domain sufficiently to be able to provide boundary conditions for new advanced models. So I think moving forward, we need to have significantly enhanced level of multi-point in situ measurements, and also remote sensing measurements that will allow full three-dimensional characterization of different plasma domain that we have in our system. So I think push toward that kind of a full 3D characterization of the heliophysics and space weather domain is going to be one of the key gaps that we need to address over the next decade or decades to come.
Okay, and then so with those, solving the problem of sparse measurements, and then also looking at these 3D measurements and models, are there any key technologies that need to be developed in the next 10 or 20, 30 years in order to address that?
Well, again, I'm really hoping that the decadal process will provide a lot of answers to this. But I do have my personal thoughts on this. I think in the context of multi-point measurements, deploying these significantly larger constellations of spacecraft than what we have done in the past, it is only possible really if we go small in terms of individual nodes of the constellation. So I really see that the miniaturization of the spacecraft platforms and pushing the technologies that allow us to do that miniaturization is one of the key challenges that we do have moving forward. And of course, from the science organization perspective, that challenge holds true also for instrument development. We need to be able to miniaturize our sensors so that we can still get high quality, meaningful scientific observations, but in terms of size, weight, and power, we can fly these instruments on these miniaturized platforms that will then ultimately allow us to deploy major constellations. So I think those are some of the key areas that, in my mind, really require some further tech development as we address the challenges for the next decade. Okay,
thank you for your thoughts on that. And I think that we're all very much anticipating what the workshop this week and discussions going forward from the community will bring in these areas as well. So I'm going to move on to a few questions for Nour. So Parker Solar Probe, incredible science already from its close flybys of the sun. And what have we learned so far that was unexpected from going there?
Parker Solar Probe, in a few words, is probably the best example of exploration at its excellence. When you fly through a region of space that you never explored before, any potential measurement you make is potentially discovered. And that's exactly what we are learning from Parker Solar Probe. If you take, for example, the magnetic, well, we know that the solar wind that is born at the base of the solar corona, it propagates outward, it gets processed along the way. When you measure it around one AU around Earth, it's pretty homogeneous. It's to a certain degree quite homogeneous. But when we get closer to the sun, it is full of this, what we call switchbacks of the magnetic field. These are basically magnetic field reversals. The field folds on its own, all the way back to the sun and back again. And this happens over the time scales of tens of seconds to sometimes several hours. The nice thing about these events that we've seen them before around 1 AU, but you see one every, I mean, they are pretty rare, but close to the sun, they are there all the time. The nice thing about them is that they are pretty energetic. They have also other properties that we don't know yet. That actually they are open question about them. But in terms of energy, they are probably the smoking gun that is at the base of the heating of the solar wind on the corona. I mean, the acceleration and heating of the solar wind plasma, which is one of the big, basically addressing two big challenges in heliophysics, which is the coronal heating and the acceleration of the solar wind. There is another also discovery that Parker Solar Probe made. Well, we launched it during the solar minimum. The sun was absolutely quiet. And when you look at the big background of energetic particles at 1 AU, it's pretty quiet. But when we got closer to the sun is actually creating energetic particles in the form of small events. You see them very often there, but when they move out, they basically get diluted. So even at the quietest times, the sun is still producing energetic events. So these events are very small, and you may say, okay, they are not relevant to space weather, but actually there are arguments out there that these small events actually create what we call the seed particles. Seed particles are energetic particles that are energized to a medium level of energy, and when big events comes along, they just take them to other level, to almost the speed of light. So these small events are also another big discovery. The other one is the dust. Dust is not really a primary science objective of Parker Solar Probe, but still, it's so important there. One of the big discoveries that we made that is almost a century old is the dust freezone around the sun. This one was predicted in 1929 by Henry Russell, and since then we tried over and over again to detect it to no success. And Parker Solar Probe gave us the very first evidence for it, that it exists. And as we get closer and closer to the sun, we will see more and more of it. And hopefully at a certain point, we will see really the clear evidence for it. There is another aspect also for dust, which is the heliospheric dust in general. We are learning a lot as we get closer to the sun about densities and about distribution of the dust, but also around the planets. You may have seen a recent discovery from Parker Solar Probe of a dust ring around the circumsolar dust ring along the orbit of Venus. This one, it's the first time we have a full picture of it all at once. That was not done before.
Thank you, Nour, for that description. Those are a lot of very big achievements. And I think that you've really demonstrated that going to a new place, this close vantage point, has significantly improved our understanding and revealed things that we either needed to confirm or didn't expect to see. So where else do we need to go in order to make similar types of advances?
Actually, you're asking really a very nice question. And well, these new observation measurements and discoveries we are making, they are answering some questions, but they are posing a ton of other questions. And that's actually the new direction we're going into. I think missions like Parker Solar Probe and Solar Orbiter, and you can build on this around for the magnetosphere and others. You made discoveries, but also you change the direction of the research. And Parker Solar Probe now is telling us, there is one thing I did not mention, that Parker Solar Probe put something in the spotlight, which is small-scale solar activity. it is hugely, hugely important. And one great example of it is the campfire that was discovered by Solar Orbiter. We are probably going down to the building blocks of solar magnetism. And that's actually the direction that these missions are telling us to go to. But there is also the large scale that we have to pay attention to. And it's gonna tell us a lot. What we are going to learn from Parker Solar Probe and Orbiter, let's say for CMEs and flares. For CMEs, we are going to learn a lot about the internal structure of these events, because from an AU, we see them, but not in much details. But when you observe them close by, you get a lot to know. You get a lot of information about their internal structure, and their internal structure is so important for their interaction with the magnetosphere. That's actually where space weather comes in. The other thing also that Parker Solar Probe and to great degree is telling us is take risks and be bold. Do not ask the right question. Go pursue them with all the enthusiasm you have. You will discover things that you never thought of. And by the way, when I gave just those few examples of discoveries, I can tell you we are making a ton of other discoveries. I'm having a hard time keeping track of all of them.
That is very good news that there are so many that you're keeping hard to keep track of all of them. We'll all be following along with them too.
Yeah.
So, I really like one of the things that you said there about as we've gone to this bold new place, overcoming technical challenges. I mean, the community just really had been envisioning a mission like Parker Solar Probe for so long, but there are significant technical challenges with going so close to the sun. The thermal challenges, of course, big success now. I really like what you said about, having to be bold and going to new places and not sure what you're going to find. And it goes back to Antti's point about this interconnectedness, because when you go and you see magnetic reconnection at a scale like this, then that's cross-cutting across a lot of different areas where magnetic reconnection occurs, right? In the Earth's magnetotail, other places that lend to this larger global picture of these dynamic processes in our solar system and in the universe in general. So, continuing along this theme of being bold, what other, technologies do we need to develop? What other places do we need to go to? Where are these bold new missions? What do you envision for them?
Well, in terms of ideas for bold missions, I think we are not at any shortage of them. Now we are thinking very seriously to send a probe that will leave the solar system in about 10, 15 years. Voyager did it in 40 years. Now we want to go way, way beyond Voyager and go into the interstellar medium. That poses other type of challenges, but still realizing Parker Solar Probe of 60 years basically is pushing the community toward, there is nothing impossible, you can do it. In terms of solar missions, there is one region that we still have to have a look at. It's the solar poles. Having a view of the solar poles, actually it's relevant also to space weather, but it's the long-term space weather. Understanding how the magnetic field behaves at the solar poles will help us to forecast solar cycles and how strong they are. That is something that we're missing. Solar Orbiter will help us to a certain degree, but there is nothing that will replace having a clear view of the poles from the top of from the north of the south poles. There is one thing I mentioned earlier as well. Space weather is an extremely complex phenomenon, and what makes it even more complex, that when you look at active regions of the sun, they seem to be separate, but they are actually connected. Sometimes you see an event happening on one active region and another event happen very soon on another active regions. There is some communication between them. We don't know. There is probably long-range connections between them. So the best way to handle this is to have a global view of the sun as a whole. And there is no way to do it unless you have a 4-pi coverage of the sun. And that's one of the mission concepts that is being thought of very, very seriously now. Having 4 spacecrafts or more to observe the sun. In terms of in situ measurements, I think Elsayed and Antti touched on this earlier. Well, we lived for so long for one single point measurements. Now the idea is to have constellations. Constellations is the way to go because you have to sample the plasma at different scales, small to very large scales. Just to give you an example for the sun, we know that whenever you have a flare of CME that is erupting from a given location from the sun, when you look at energetic particle in the heliosphere, they almost spread at all longitudes. So having those constellations will help us understand how energetic particles are crossing fields and how they are spreading.
Thank you for that perspective. And I was glad to hear you mention all of those different concepts. I mean, of course, we've heard just resounding input from the community that we need to be looking at the poles. You know, there was several workshops about this within the past few years, a lot of white papers about that this week. Also, looking at the sun in 4 pi, I mean, we saw a number of presentations about that at the Future Space Weather Infrastructure Workshop that was hosted by NOAA at the National Academies. And we heard that from the community as well, especially with looking at large scale structures. And then of course, the distributed measurements as well, where we just have such a large swath of space and just so few measurements in between us and the sun and within geospace. So thank you. And then of course, going out past our solar system, which is just an incredible concept. So I'm going to move on to Elsayed. A few questions for you. So I really enjoyed your presentation, and you had highlighted that NOAA's future plans include space weather as a third and independent leg of its architecture. Can you tell us what the importance of this is, and really the impact that you think that it's going to have within the community?
I do feel that this is a significant development, and it recognizes the increasing importance of space weather and the dangers that it poses to our critical infrastructure. We're an operational agency, so we put our resources where it would have most impact in protecting our nation's lives and well-being. And so it recognizes also that the current observing architecture has been an ad hoc assemblage of space assets that provide information, and the system we want to plan will provide resiliency. The current system doesn't provide resiliency. It relies on assets that are not designed for operational mission and are decades beyond their mission design life, and really lack continuity. This is something by putting us as a pillar in our observing system. It commits NOAA to maintaining the observations that we're leveraging right now, or hosting right now, and also committing NOAA to the Sun-Earth line to make the upstream measurements and imagery that's needed for our predictive capability. As I mentioned, as we're planning our next generation space weather architecture, we want to provide that robust system capability. Our first step has been to immediately implement the known weakness in our ad hoc infrastructure, which is the upstream solar wind measurements and the coronal mass ejection imaging. And so that's why we developed the current space weather follow-on program to address those issues. But we are planning for the kind of diverse kind of observations, hopefully leveraging constellations with partners or implement them on our own to make the necessary space weather observations across the whole system. I also want to point out that having these measurements provide that infrastructure that are needed for research and models as well. So we all know that the solar wind inputs are what drive the near Earth models, the geospace models, magnetospheric and ionospheric models, and they also and then the imagery is also what helps drive the solar and heliospheric models as well. So NOAA is going to be providing those so that the research can be done, can drive the research, but also the research agencies can focus on new and improved observations.
And thank you for bringing up new and improved observations. And it ties in with so much of the discussion that we've had already in this session around, how the science is still evolving behind space weather. And it seems like a challenging task to plan a future architecture, when things have the potential to change. So how does NOAA deal with that and incorporate this new and evolving science?
Well, I think the history of space weather has been, is and will be a real research to operations story. When ACE and SOHO demonstrated the utility of upstream measurements as well as solar and coronal imagery, and then that's now the lessons we've learned to develop the Discover spacecraft and now the Space Weather Follow-on program. And same thing with the instruments that we have in geostationary as well. Research has demonstrated SDO was the predecessor of the SUVI instrument that monitors the sun 24/7 for space weather centers. And we're learning now, for instance, from the NASA GOLD mission, which is imaging the thermosphere and ionosphere. And hopefully NOAA is going to incorporate that very soon into its operational capability. And we are planning, once it's in our customer, which is the Space Weather Prediction Center, when it's their capability that they need maintained and it fulfills their requirements, we figure out how to get it to them, whether deploying our own systems or with partnerships. And so we look forward to seeing what new developments are going to come out of ICON, GDC, in terms of knowledge that we can apply to our defining our observing system. One last example in the ionospheric realm is what we had with COSMIC, where it was a real pathfinder for ionospheric measurements and ionospheric radio occultation. And that's been succeeded with COSMIC 2, which NOAA partners with the US Air Force and Space Force and Taiwan for a real operational mission. And then we're looking again to continue that through both a government backbone and commercial data buys, et cetera.
Thank you. And then, kind of drawing out that government backbone piece that you mentioned as well, you're a member of the Space Weather Operations Research and Mitigation Group, or called SWARM. And can you discuss what this group's work is to understand space weather forecasting and make sure that we have preparedness needs, that our preparedness needs are met?
Yeah, SWARM has been a real effective effort and forum for galvanizing the space weather effort within the government. I mean, it has been a real success story for interagency cooperation and collaboration that looks at space weather from the research side all the way to the operation and preparedness. An emergency response and back and forth, they don't just meet in the middle. They start from one end and go to the other and back and forth. And so part of it has been a key part of it has been a working group that on developing, disseminating accurate and timely space weather characterization and forecasts. That's both on the observations and on modeling and forecasting. And so we have a lot of actions that interagency groups work on for enhancing current space weather models, developing model techniques for space weather testing and validation and forecasts. And what these groups do is define kind of the infrastructure and the activities that engage the community, engage the science community and industry and our end users on what forecasting and modeling advancements are needed. And that's and key tasks are enhancing data integration, utilization, developing metrics to measure and evaluate the performance capabilities of operational and scientific models, and supporting research and development to improve models. And so part of this is developing the research and development strategy across the agencies, specifically NASA and NSF, but also DoD and NOAA on how to improve models. We've created a infrastructure with Goddard, between the Space Weather Prediction Center and Goddard, that provides a test bed and proving grounds for different models from the community, to look at where the advancements are needed, and also develop forecasting with existing models. And we're leveraging, again, the larger scientific community through COSPAR and Living with the Star, et cetera, for advancements in forecasting. And that's all kind of driven by SWARM, but also leveraged by SWARM as well.
Thank you for that description of the working group. There's just so much important work going on across the agencies, within the research, operations, modeling, all of these different communities. And so thank you to the three of you for really drawing that out and walking us through this dynamic and evolving landscape. I know I could continue asking you questions the entire time, but let's turn it over to the community and see if there's anybody, any other questions in the chat. Alan, I'll turn it back over to you for that.
Okay, thank you. We do have one or two things we can get to in the few minutes we have left over. First, go for Elsayed. And you talked about the new NOAA focus on weather forecasting. I don't want to say prediction. Predictions is different than forecasting. So I think you said weather forecasting. And you said several times that NOAA is an operational organization. We talked a lot about different data, different observations, different ways of advancing the science. But now when we get to NOAA, what is the practical application of all of this? How are you taking this in your operational environment and applying it to people's lives every day as you go to your new charge?
So the space weather observations that we make and plan to make are primarily fed into the Space Weather Prediction Center which is part of NOAA and part of the National Weather Service. And it provides alerts, warnings, and forecasts to a diverse user group. That includes airlines. There's the International Civil Aviation Organization that has a space weather, that has a global space weather alert system for all the civil aviation partners, and including, and also maybe arguably most important, the power grid, which needs to know the space weather conditions for any geomagnetically induced currents that it can affect power supply across the country. The Congressional Budget Office estimated that a severe space weather storm, while it's a rare event, can affect our power system and cause upwards of $1 trillion in damage. And even a moderate space weather storm can cause billions of dollars in damage. So this is a key customer for us, an end user for us, that protects us there. And there's also a whole other diverse user group, including navigation and communication, because the space weather affects the ionosphere, and that affects GPS signals and high frequency communication as well. Precision agriculture is one that has been growing over the last few decades, that use this system for their operations, and they lose lots of economic vitality when these systems are down, and so when they have errors in the GPS measurements or observations. So hopefully that answers the questions about what how it can impact us on a day-to-day basis.
You could take an hour or two to describe it all, but thank you. Yes, it starts to answer those questions. We'll start this with Antti and maybe move through the rest of you as we close it out. You talked about the 2024 decadal survey. I've worked in human spaceflight for a number of years, and I'm used to programs and things being aspirational instead of being practical. What do we need to do to support things that are going to come out of the 2024 decadal survey so that we are able to achieve them instead of it being an aspirational plan that nobody can achieve? What kind of resources do you need? What kind of interest do you need? What kind of focus do you need?
Well, I mean, I think, it's a very good and complex question, and there are multiple dimensions to this, but maybe I'll address a couple of dimensions, and one of them pertaining specifically to space weather. I think aspirational in the context of the decadal, and certainly, for example, in the context of the Helio 2050, which is a kind of a multi-decadal vision forward. We need to dare to dream big as well, and it's these big ideas and aspirations that make our field and our scientific research really exciting. Exciting not only to us but also to the general public and the decision makers. Way above my pay grade. So I certainly personally hope that we dare to dream big as a part of our scientific research goals in our decadal survey process. From the space weather standpoint, what I think, and I think the community agrees with this, is really critical, is that we have a very strong end user showing and end user participation, end user voice as a part of our decadal survey process. I think it's the end user voice that emphasizes the national and quite frankly international need for investments in the next generation technologies and the processes that allow us to push this new research understanding to the operational organizations like Nour. So I think and that may be something that was missing from our previous decadal. I certainly hope that the next decadal will have this very strong end user voice that to some degree helps to validate our messaging that space weather and the space weather impacts are really important, which of course then also ties to what Elsayed was just talking about, for example, the impact on the power grids.
Thank you, sir. One final question for Nour, and we have about 1 minute to do this. You talked about advances in forecasting and solar activity. What do you think is going to change over the next 10 years? Past 10 years, we've had a certain amount of change. What kind of changes do you think we're going to get in the next 10 years based upon what you're seeing in systems and capabilities and instrumentation?
I think this coming decade is probably a golden decade for heliophysics as far as the sun and any heliospheres are concerned. With Solar Orbiter, we will have the first view of the solar poles. That is really something that we have been looking for a long time. With Parker Solar Probe, we're going to the source of the solar event, and that's something that is very, very important to all the processes. By the way, when we talk about big CMEs and their propagation toward Earth and beyond, they depend on the background solar event, and understanding how the solar wind evolves is really important. There is also another thing that we are going to learn, and it's we will get the highest resolution observation of the solar magnetic field. What we have been living with for many years now is kind of moderate resolution by today's standards. And they will not lead you to discover the building block of solar magnetism that is at the basis of all the processes that are ongoing in the solar atmosphere. With DKIST, I think we're going to do that. You are muted, Alan.
Unmuting first. Unmuting helps, doesn't it? Thank you, Nour. Guys, this has been a superb panel. Nicole, thank you for moderating it. And Nicole, Assad, and Antti. Thank you very much for being in the panel. Audience, I'm sure actually learned probably more than I, because I'm just a dumb engineer, but it was really fascinating what I could follow. So our next session is going to be moving out. So our audience should go ahead and go into the
application and select for the next session, and it'll be starting right now.
Thank you.